Hi everyone, we're Group 13, and today we'll be presenting our use case, which is heavily inspired by Singapore's endemic approach to COVID. With the gradual easing of borders and the increasing rate of vaccination globally, we expect more and more business and leisure travelers coming into Singapore. In line with this, Changi Travel's business proposition is simple: a shuttle bus package that offers safe, convenient, and time-guaranteed transit from Changi Airport to targeted drop-off points near a traveler's hotel of choice. With a service coverage spanning close to over 400 hotels, we will be using a capacitated vehicle routing model to optimize our business operations and streamline the customer experience. The model has a few moving parts. 1, a fixed starting node with a stochastic demand. In this case, our fixed node is Changi Airport. 2, a fleet of buses of a specific capacity type. In our case, 50-seater buses. 3, we have service routes that are dynamically determined based on where passengers for a particular time window are billeted. 4, a time guarantee for passengers to be dropped off within 45 minutes. And 5, a similar time guarantee for buses to return to the airport within an hour's time. For the sake of simplicity, the model makes a few assumptions. To begin with, demand is something that is a stochastic function of arriving passengers, the capacity of their hotel of choice, and the time of day by which they arrive in Singapore. Bus demand is likewise normally distributed. With respect to travel time, we also assume that travel time is constant throughout the day and throughout the week. Likewise, it is considered that the distance and time taken between two nodes is symmetric, which means that time and distance from A to B and B to A are exactly equal. Overall, we have two main objectives. First, we want to determine the optimal number of routes and the drop-off points for each of these routes, while respecting the time guarantees that we've initially set. And flowing from this first objective, we have a secondary goal, which is to determine the optimal number of buses needed to run the operation. Given the stage-wise reopening strategy of government, this number will need to be recalibrated every so often to ensure that we have sufficient leased buses to keep up with demand and realize the time guarantees we've set out in our business proposition. Over the next few minutes, we'll be taking you through each of those components in more detail and show how they all fit into the overall model.
Over the next few slides, we will be talking about some dataset transformations, as well as model particulars such as node and arc configurations, which of course translate to hotels and roads. Specifically, we will expand on how we defined pickup nodes, drop-off nodes, how we estimate node demands at particular times of day, and finally, how we obtain real arc lengths. As previously mentioned, the model will determine the optimal number of routes and hotels to visit in order to optimize for travel time while meeting demand and time service guarantees. This implies all shuttle bus services will depart and return to a starting point. The starting point for this service is Changi Airport, from where passengers will be picked up and taken to their hotels. In order to simulate passenger demand for the service, flight arrival information as well as hotel room capacity were used. We will talk more about this in a few minutes. Regarding hotel locations or drop-off nodes, two major transformations are done to the dataset. First, the shuttle bus service area is limited to downtown Singapore. This way, outlier hotels to the west of Singapore are not considered, as they have a relatively low demand and would not meet our previously defined service guarantees. Second, the dataset is simplified by conducting a K-medoid clustering on all hotel locations. This allows for the creation of K-service zones with a real hotel location at its center to serve as a drop-off point. This implies that for this specific implementation, demand is aggregated for each zone, and passengers would move to their final destination after being dropped off. Of course, this same model can be easily expanded to include K-centroids, potentially one for each hotel, if the service were to be expanded as a future business model. Here, it's possible to see the drop-off points for each of the service zones defined in the current business model. Each hotel represents a center for each cluster as defined by the K-medoids model. To simulate the mean drop-off demand of passengers at each service zone for a particular time window, we used a combination of each hotel's total room capacity multiplied by a factor of 0.05, as well as a time window multiplier, representing the time of day we are estimating. In order to account for risk and real-time variations, we carry out a stochastic modeling, where the demand for each node follows a normal distribution with a mean defined by the previously mentioned equation and a standard deviation. Expanding on the demand estimation model, we simulate for 24 time windows, representing each 1 hour of the day. The table on the right provides information on the multiplier used for each time window. The multiplier is calculated based on arrival flight information for Changi Airport, observing the time distribution across 3 distinct days of flight arrivals. We can see the service expects very different demands depending on the time of day, with demand estimations available for 24 hours of the day. As mentioned previously, this information serves to calculate the mean hotel demand, which is assumed to be normally distributed in our stochastic modeling. The final component of input data is the distance calculation or arc length for the hotel and airport node network. We obtain the complete network graph for all nodes and obtain both the real time and distance in between each node using the Google Distance Matrix API. For this model, we decided to optimize based on the time element in between each arc, noting that it is assumed that with travel time between node A to node B and node B to node A are the same.
Our model is a modified vehicle routing problem designed to choose the best routes to maximize time savings. The main decision variable that we are solving for are the arcs that are used for each route, as well as the optimal number of routes for each time window. Along with the time taken for each arc and the demands for each hotel, we also input the maximum capacity of the bus, the guaranteed time by which visitors are dropped off to their respective hotels, and the time by which the bus is expected to return to Changi so that it can be ready for its next trip. Our model's objective function is designed to maximize savings. It computes a savings by considering the time saved if any 2 nodes are joined to be serviced by one route instead of returning to the airport in between them. Our constraints ensure that the optimal number of buses leave Changi Airport and also return to Changi Airport, and that each hotel is serviced only once. Similar to a traveling salesman problem, we use the number of people dropped off at each stop and time taken as an increasing variable to ensure that we have no subroutes. We also account for the maximum capacity of a bus to ensure that the total demand for each route does not exceed it. Time constraints are included to ensure that the longest time to reach a hotel does not exceed the guaranteed time of 45 minutes, and also to ensure that the bus returns to the depot within 1 hour. We ran a few preliminary rounds for our model for various time windows. The results here show the optimal routes for time window 15, which is from 3 to 4 p.m., time window 17, which is 5 to 6 p.m., and time window 21, which is 9 to 10 p.m. As we can see, the routes are all different for all of them. 9 to 10 p.m. has the highest demand among the 3 and therefore needs 6 bus routes, while the other 2 time windows need only 5. This demonstrates how demand affects the results of the model. The time constraint also affects the number of routes. In the 3 time windows here, we notice that there is a single route to the bottom of the map. This is because this hotel cluster is located in Sentosa Island and is further away from the rest of the hotels, and also quite far from Changi Airport. Therefore, it needs to be served by a single route, so it can return to Changi Airport within an hour. As we can see, the model is quite flexible and the routes will change based on varying demands and various time constraints. In the future, we can consider a few ways to improve and add on to our model. One of our primary assumptions is that travel time remains constant throughout the day. In future models, we can consider traffic data to understand how travel time varies throughout the day and incorporate peak hours into the model. Since some hotel clusters may have a significantly lower or higher demand, we can also consider using buses with multiple types of capacities and assigning which routes need which type of bus. Our current bus routes travel between hotels and airports, so another way to improve our model is to consider passenger travel in both directions. We don't just consider travel from the airport to the hotels, but also travel from hotels to airports. So therefore, we're including drop-offs as well as pickups. We can also use this model to expand our drop-off locations to more hotels, and also to other types of locations like tourist attractions. Finally, if some clusters have extremely high demand, another improvement is to dynamically change the number of clusters instead of using a predetermined number of clusters as we did here. That's all we have for our proposal today. More details about our project and model can be found in our term paper. Thank you for your time.